shall begin. Alright, quiet down, you guys. We will continue on. I'm going to go into the beginning part of chapter 2. And depending on if we have time or not, I might take a small jump to chapter 12. Okay? Turn this back on. Alright, is that better? Okay, great. So we will, I will take, we'll go into chapter 2, first half of chapter 2, and depending on whether we have time or not, might take a small detour to chapter 12. Chapter 12 is kind of this standalone section that we have to cover when we make an appearance on the final. So actually, before I get into chapter 2, let me just mention a few more things about observational studies and experiments. They are covered more thoroughly in your reading, okay? I feel like it's easy enough to read through those sections in the book and get the detail on observational studies and experiments on your own. If you have any questions about that, don't hesitate to ask your questions. It mentions topics such as placebos and blinding. Placebos and blinding are used in experiments in order to make people unaware of which treatment they are receiving. So, in experiments, we also use placebos. Again, covered in your reading, so be sure to do that. All right, so chapter 2, we will talk about visualizing numeric data. So let's say we've gone out and we've gathered a bunch of numeric data. So, if you will indulge me, maybe I can just ask a few of you students to just tell me how many siblings you have. Okay, so if I ask you how many siblings do you have, that is a numeric variable because you are telling me how many, and your answer will be I have 0 siblings, or I have 1 sibling, or 2 siblings. And if you don't want to tell me the truth, you don't have to tell me the truth. That doesn't matter. I'm just trying to gather some data so we can do the visualization here. Okay, so how many siblings? And maybe in a traditional data set, we would say case 1, case 2, or this person's name, that person's name. But in this case, we're just going for one variable, how many siblings, so just call out that number, and now we'll write this down here. So maybe I could begin with you. 1 sibling, okay? And again, if you feel this is too personal and you don't want to answer it, you don't have to answer. We'll just 1, okay. 3.
4.
4. 4. Ethan. 1. And then 2. 2. And wait, 3. 2.
One.
1. And Sarah, 4. 4. 10.
Who was that?
Okay, and you 0. 0. Okay, alright, so this will serve as our data set, okay? And again, this is not truly a case table because a case table would have 1 row per person, but because my chalkboard is only this tall, I've put my rows as such. Okay, so what is my sample size?
17.
17, let me count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So in this case, I have 17 people. Okay. So one simple way to visualize our data set is with a dot plot. Okay. A dot plot has a horizontal axis, and this is an important thing to note. For any visualization of numeric data, generally the horizontal, but sometimes the vertical axis, at least one of the axes will be numbers. Okay? One of the axes will be the values, represent the values that this variable can take on. So one axis will be the values of the variable. Okay. So in this case, my horizontal axis will be number of siblings. And what kind of values can the number of this variable take on? Well, the smallest number will be 0. Okay. Then we have 1, 2, perhaps 1. Okay, so the number of siblings will form our horizontal axis. And with a dot plot, we will put a dot on each value that shows up in our data. Okay? So our first value was 1. Put a dot there. The next value was 1. The next value is 3. The next value is 4. And I'm going to just continue this, putting more dots here. Give a little more space. So this is my dot plot. Does this make sense to everybody?
Yes.
Okay. Are there any questions on how my dot plot is formed? Okay, so every case, every person in this table is represented by a dot here, and we can see which values are most common. Okay, so it seems that the most common number of siblings is 1. So, and we have 8 people with 1 sibling. And so there we have a dot plot. When you have a large data set. Sometimes it is inconvenient or difficult to understand when you have a ton of dots. So you can imagine I interviewed the entire classroom how many siblings we have, and if there's 80 of you students, then I would have 80 dots on my dot plot. And that might be too many dots for us to appreciate. So another thing is the histogram. Histogram is very similar to a dot plot, but rather than dots, we have bars. And our vertical axis, the height of our bar, will be the frequency. Go across my horizontal axis here. So the vertical axis is frequency, the horizontal axis will be, okay? So for all numeric data, one axis will always be the values that the variable contains. So same thing here, 0, 1, number of siblings. All right, and because we've already created a dot plot, our histogram is very easy to make. At 0, we have one person represented. With one sibling, we have 8 people represented. There are 2 people represented with 2 siblings, so the bar at 2 goes up to level 2. 2 people with 3 siblings, 3 people with 4 siblings, and then 1 person with 10 siblings. So this is our histogram. So, what does this bar right here represent? What does this tell us? So the bar has a height of 3. And what does that mean? It means that there are 3 people in our data set that have 4 siblings. Okay. So just so we understand is that there are 3 people data, height of the bar. I have 4 siblings. Location. Is that okay? All right. The thing about histograms, and this might not be the best example to do this kind of transformation, but with histograms we can change the width of our bar. Okay, so with something like number of siblings, you probably won't need to do this operation, but I'm going to do it just to illustrate it. It will be more useful in something where we measure people's weights. Okay? If I ask you what your weight is, and let's say that was not a taboo question, and you guys can freely tell me what your weight is, and most of you would probably round off to the nearest 5 pounds if you were to give me your weight in pounds. Okay? But the truth is if you were to step on a scale, you probably don't weigh exactly 145 pounds. You probably would weigh 146.2 pounds or 143.8 pounds or something, okay? We don't know, okay? And so let's say we had everybody step on a scale and we recorded all of these weights. Okay. So we might have someone weighing 143.2 and 144.8 and 163.8 or whatever. In that case, if I drew a dot at every single value, I would have one dot at 143.2, and I would have another dot at 144.6 or something. And that would be a very, I guess maybe that dot plot would be too detailed. We're making distinctions between people who weigh very close in weight, but maybe for all intents and purposes, we could say they are about the same weight. So with a histogram, you can group people together. And you can say, rather than saying, I have one person who weighs 143.2 pounds, and I have one person who weighs 144.6 pounds, and I have one person who weighs 161 point whatever, you can say, I have two people who weigh between 140 and 150 pounds. Does that make sense? And so with a histogram, we can create what we would call wider bins. Okay, so with histograms, we can change the bin width. We can make it wide or narrow as we see fit. So in our, just for illustration, we could say, for the data that we have, I could create a bin that says between 0 and 1 siblings, between 2 and 3 siblings, between 4 and 5, 6 and 7, 8 and 9, 10 and 11 siblings, okay? This is just for illustrative purposes because in real life you probably wouldn't do this. It would make a lot more sense for something like someone's weight data. But we would have the bin and we would have the frequency. And so from our data set, how many people would be in the bin of 0 to 1 sibling? 9 people. Okay, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, or if we were to look at my data set, I would count 9 people that have 0 or 1 sibling. How many people would be in the bin for 2 to 3? 4. How many people in the bin for 4 to 5? 3. Okay, and I would have 0, 0, and 1. Questions? What would my vertical axis be? Frequency. Times 2, 3, 4, 5, 6. Now it started at 0, and convention goes, you would just do the left bin. Okay, so I would go from 0, and then the next bin begins at 2. The next bin begins at 4, and so my axis would look like this. And this first one would go up to 9. 1, 2, 3, 4. This one would go up to 4. This one goes up to 3. And then we have 1. So I have changed the width of my bin. This histogram and this histogram both have the same underlying data, which are these 17 people that I've asked. But they look different, okay? There's some similarities, but there's definitely differences, and that all depends on how we've changed the bin. Is that okay? Okay, just a quick recap or check of our understanding. We use histograms for what kind of data? Numeric data. Okay, what are the types of data that are available? What are the two types of data? Okay, categorical data, numeric data. All right. We've learned about histograms and dot plots. This okay? What does the letter N represent? Sample size. All right, so in large data sets, or really any data set, we can create a histogram. And if we were to create a histogram for the number of siblings, and if we were to ask many, many people, what I would probably see is something that looks like this. The number of siblings. 0, 1, 2, 3. And of course, this frequency. So perhaps if I ask many more people how many siblings they have, it might look something like that, where one sibling is probably going to be far and away the most common number of siblings, but we will have a good amount of people with 2 or 3. But as the number of siblings increases, we will probably see fewer and fewer people. Okay? And we'll also see some people with 0 siblings. With histograms, okay, again, this represents a set of data. Okay, so there might be 100 people represented in this data set, or maybe 200 people, depending on how many people I've asked. Okay. We might ask the question, what is the distribution of data? Might sound like a weird question, but that's basically asking, can you summarize what this histogram looks like with words? Okay? The data, in this case, is the number of siblings that we have, and that's the data. What is the distribution? In this case, the distribution is what do the numbers and the data look like without actually listing off all the numbers. What is the distribution data? Data, basically we're asking what does the histogram look like? Okay. And in this case, what we see is we've got a lot of people with 1 sibling, some with 2 or more, but as we have more and more siblings, we see fewer and fewer people with that many siblings. And that, I hope, it matches our intuitive sense of family size. Perhaps if we were to ask this question maybe 30 years ago, what do you think the distribution would look like then? Yeah.
6 children inside?
Yeah, so 30 years ago or so, people who attended college would be part of what today we call the boomer generation, where it was a lot more common for families to have 4 or 5 children. Okay, today the average family size is 2 or 3 children in a household. Some households are larger, have more children, some have fewer. So we see a distribution like this. Maybe 30 years ago, if we asked students in college, how many siblings do you have? A more common answer might be 4 siblings or 5 siblings. Some would have 3, some would have more, some would have less. But the distribution would look different. Okay? So if we ask, what does the histogram look like? There are a few things we want to talk about. Okay? One is what we would call the center. Alright. And so the center, we have the idea of the middle point or the halfway point. The other name for that is the median. Or we also have the balancing point. Which is the mean. So in this case, let's talk about the balancing point. The idea here is, imagine this thing, if I were to cut this out of the board, or if I were to have blocks that were this tall, equally this size, and I were to try to balance this on a seesaw. So I've got the little fulcrum, the triangle. Where would I want to put that balancing point so the thing stays balanced? Okay, if I put it over here, what would happen? This thing would tip over like this. Okay, and if I put it over here, what would happen? The thing would fall like that. So around where would I need to balance this?
In between.
Okay, I would say right around, maybe with this way I drew my picture poorly. Yeah, somewhere between 2 and 3. Okay, that means my picture is inaccurate, but yeah, maybe we would try to balance it right here or something, okay? And so that means, in our picture, this would be the mean. And maybe it's not going to be balanced there.
More to the right.
Yeah, it's more to the right, I agree. Somewhere, okay. My inaccurate graph of made-up data might not have the most accurate balancing point. Okay. Life is hard. The halfway point is, pick the point where about half the data is larger and half the data is smaller. Now sometimes it's very close to the balancing point, but the halfway point is, if you were to paint this thing from left to right, okay, at exactly what point would you have used half of the paint that you need? That's the halfway point. Okay. So if we were to shade this whole thing, where would I have used half the paint? So, right there? I don't know. Okay. Again, my picture, not the most accurate thing. I apologize. I hope you don't hold that against me. But that would be the halfway point. That would be the median. Okay. A lot of times they're very similar. Sometimes they're a little bit different. So if someone asks, what is the distribution of data? you would want to mention the center, and you would say something like, the central point, center is around 2 to 3, according to this picture. Yes,
That'd be the same for the other picture?
this one?
Yeah.
Yeah, I don't know. Where would our balancing point be? Here? Who knows? Yeah, something around there. I don't know. Yeah, it's a little easier to count the halfway point. Yeah, I've got 1, 3, 4. I've got a total of 8 people past here, and I've got 9 people past here. So my halfway point would be like just a tiny bit to the left of 2. Concept of center here, okay? Yes.
So to determine the halfway point, we can also go back to the graph that we made, like the frequency.
Yeah, if you have the actual frequency table, you could use that to determine your halfway point. But sometimes you're just given the picture of the histogram,
We would just estimate.
and you would just kind of eyeball it.
So
Yes.
is a frequency table, a histogram, a dot plot, these are all distributions of data? Or are they termed as methodology of how to distribute,
So the distribution of data is
how it's placed
the
on?
data itself, okay? A histogram is one way to visualize
To
the
visualize.
distribution. The dot plot is another way to visualize the distribution,
Okay,
this-
you mean to make visible?
to make visible.
Thank
The
you.
frequency table is a way to show, not with a visible picture, but with a table.
Okay.
So, what would a comparable idea be? Okay. This might not be the best expression, but we have thoughts in our brain, and to express that thought, I talk. Okay. And in a similar sense, the data is there, but in order to, I guess, express or visualize,
data.
we have tools. We have histograms and dot plots. I can express my thoughts through speech, through gestures, through song, maybe. All right. Well, anyway, back to this. So, if someone asks, what's the distribution of data, you would want to make sure to mention the center. Another thing we want to talk about is the shape. Okay. And when we talk about shape, there are 2 things we want to talk about. We want to talk about the number of peaks and the symmetry. So when we talk about the number of peaks, that would be how many hilltops do we see. So if I were to just kind of make a smooth curve of what this thing looks like, maybe it looks something like this. I would draw, let's say my histogram looks kind of like this curve. And how many hilltops do I have there? I've got 1. So this would be a distribution with 1 peak. And we would call that unimodal. Mode being the peak. I could have a distribution with 2 peaks. we call that? Bimodal. And if we have any more than that, 3 or more, technically I suppose you could say trimodal, although nobody really says that. We just say multimodal, okay? So it's a 1, 2, or many. Unimodal, bimodal, multimodal. So bimodal might be something like this. Can you think of anything that is bimodal? I'm sorry?
Like, what do you do in the wall space? The nat, like, what if, I'm so losing
Okay.
Like nat, like the. NASDAQ
So whilst I think you're talking more like a time series of data, which would not be an example I'm looking for, yeah.
Could it be the average weight of a man versus a woman, or the average height?
Okay, so average weight and average height could be bimodal. When you actually look at the data, it looks a little bit more unimodal because there are a lot of people who are in between the heights. But that would be a good example. And so actually I will expand on that and I will say testosterone levels would be bimodal, okay? So testosterone level is a numeric variable, okay? We could take a saliva sample and measure how many milligrams or, I don't know, picograms of testosterone per, in your saliva. We can get that. And what we would see is, remember, this is a numeric variable, and so we would see some people with large amounts of testosterone, some people with lower amounts of testosterone. Okay? And if we were to graph all of that data, we would probably see 2 peaks. This peak, with the higher level of testosterone, would represent the average amount of testosterone in a male. There are some men with higher levels of testosterone than other men, and there are some men with lower levels of testosterone than other men. But most men would be kind of in this average testosterone level. Over here, this would be the average testosterone level of a woman, okay? So men and women both produce testosterone, but men in larger quantities. And so over here would be the average amount of testosterone in a woman. Some women have more testosterone than other women. Some women have lower testosterone than other women, okay? But generally, even for a woman who has high testosterone, her levels of testosterone generally are not higher than that of a man, okay? So we have a question.
So this is based off of samples and like either studies or experiments, right? So it's
Yeah.
nothing to do with like a timeline or anything.
Yeah, this is just data collected,
Okay.
okay? Yeah, yes.
Could a bimodal chart show the difference between basically deaths during one war compared to a different war?
I'm not sure what you were talking about, I'm sorry.
For example, you'll have a bimodal chart. But it will be separated into 2 different dates with different amounts of deaths during.
Okay, so you were talking, you have, in that case, you do not have one variable here, okay? You have, so this is a distribution for one numeric variable. What you are mentioning is one numeric variable, which would be the amount of debt, and a second variable, which is the date, okay? This, what we're talking about here, would not apply on that situation, okay? Yes?
Doesn't this have a second variable as well, the gender, male and female?
So there is the gender is the reason why we are seeing a bimodal distribution, But if you are thinking of the actual data that we've collected, all I have here is testosterone level. And I just threw them all in one batch here, okay? And so maybe someone, I'm making up numbers, I have no idea what testosterone numbers look like. All right, whatever, okay, so somehow this is the testosterone levels that we are recording and we got this, all right? Here, we are not distinguishing between male testosterone level, testosterone from a man or a woman. We're just saying, these are testosterone levels of people. Let's make a histogram that we've smoothed out as a curve. What does it look like? It looks like this. If I were to say, oh, this one belongs to a male and this one belongs to a female, what I could do is I could create one histogram just for males and it would probably look like this. This would be the male histogram that's smoothed out, and one histogram for the females, and it would look like this. Okay? But then when we throw them all together, what we get is bimodal distribution. Does that make sense? Yes.
Will it ever be where they're not even, but it's still considered a bimodal?
Yeah, it doesn't have to be even, okay? It could be, I don't know. You could have a distribution that looks like this, and that would be bimodal, okay? Because it looks like there's two hilltops. One hilltop is just big. So when we're talking about shape, we've got the number of peaks, unimodal, bimodal. If you have more than that, multimodal. Yes.
Can you just like do another example similar to that with the variable? Because it kind of threw me off as you mentioned.
Okay, that's good. All right. So another example of bimodal distribution, or
Because it threw me off when you mentioned female and male. Like then I started thinking about two variables and I just got confused.
okay. So remember when we're making histograms, and I hope it's okay that I'm representing histograms with just smooth curves, but underlying it's really a bunch of bars. Is that okay? All right. So we are representing one numeric variable. Okay, so again we have one numeric variable. All right. And maybe we ask someone, I think what a good example is. Can we see how many piercings do you have? I have no idea. And that's what we went around the classroom. We're not going to do this. All right, but we say, how many piercings do you have? Someone says, I've got 2. All right. So this would be all piercings, ear piercings, body piercings. Leave it at that. Okay. How many piercings do you have? We have, someone says, oh, I've got 2 piercings. Someone says, I've got 0, and I've got 0, and someone says, I have 8, and 3, and whatever, 1. Okay, all right. I don't, okay, so we're probably going to have a lot of people with 0 piercings. All right. So that actually might be the most common number of piercings. So if I make a histogram, I would have a large peak at 0, okay? Do you think I would have a lot of people with just 1 piercing? Probably, I mean there will be some, but not very many, okay? But there will probably be a lot more people with, let's say, 2 piercings than 1, okay? And 3, and so I would have 3, probably not very many, and 4, and something, I don't know. whatever, okay, so my histogram might look something like this. Is that okay? And maybe at some point, you got these things that look like that, I don't know. This technically would be a multimodal distribution. Okay, I've got a peak here, another peak, and so on and so forth. Does that help? Okay.
So for multi-modal, that the frequency doesn't have to be so high, like, because you're comparing, like you will make like a little hope from 0 to 1, and
Yeah,
then
yeah.
2 to 3 or 4 to, you know what I mean?
Hill and then
Okay.
whatever.
So multi doesn't necessarily mean super high, it could be just.
No, multimodal just means more than 2 hills.
Okay, so
Okay.
it doesn't matter how high, okay.
Yeah. You could have equally high peaks. You could have something, three peaks in both of those cases, okay? Alright, so that's one thing we talk about when we talk about shape. Is that a question there? Okay. Just a scratchy. And the other part is the symmetry. And we have symmetric. We have left skew, right skew, uniform, and none of the above, I guess. Alright. So symmetric would be anything where you can kind of stick a mirror in the middle, and it looks the same on the left and the right. So that would be symmetric. Okay, so these are both symmetric. Left skew, looks like this. And right skew looks like that. What does it mean to be right skewed? Well, number of siblings is an example of a right skewed distribution. It means most people exist kind of on this lower end, down here. And we have some with very high values. Okay. But nobody, so this is like the middle point. We've got, you don't have anybody that's too much lower in the middle, although you do have some people who are much higher in the middle. Okay, so if we said the middle point is like 2 siblings, you don't have anybody with more than 2 units away from the middle, okay? Because the lowest number of siblings you can have is 0. You're not going to have anybody that's more than 2 units away from the middle. But is it possible for someone to have 10 siblings? Yes, and that person is 8 units above the middle. Does that make sense? Can you think of anything else that might be right skewed or left skewed for that matter? So remember, we're thinking of a numeric variable. We're talking about either left or right. Yes?
How many times somebody drinks water?
How many times somebody drinks water a day? I would argue that that would be symmetric, okay? Being that most people drink water, I don't know, 5 times a day or something. Some people will drink more than that, some people will drink less than that. But probably you will have just about as many people who have 8 drinks, that would be 3 drinks above average of 5, as you do people who have just 2. Yes.
How many pets allowed?
How many
Or
pets?
people?
Yeah, that could be right skewed. Yeah? What, red shirt.
Right-handed people with left-handed people.
Okay, right-handed people versus left-handed people. What kind of variable is that? That would be a categorical variable, okay?
Oh, yeah.
So these distributions, these shapes and these things, these only apply to numeric distributions, okay? Yeah.
Grade on an exam,
Grade on exam, would that be right skewed or left skewed?
depending on what the scale starts. Could be on the left.
Okay, so I would say grade on an exam would be a good example of a left skewed distribution, okay? Maybe the average exam score is like an 80%, okay? Highest grade, probably 100%, maybe a little higher than that. So the highest grade is only 20 points above average. But will I see people with 20% or 30%? Sure, those people are 60 points below average. So I would say grade on exam would be the left skewed distribution. Yeah, we'll do one more example now. Yes.
How many days people drink out of the week?
How many days people drink out of the week? So the number there is going to be between 0 and 7. Yeah, probably right skewed. Okay. So what it means? Okay. Number of days someone drinks out of the week can take on the values between 0 and 7, right? 0,
Number
1.
of days would be X, I mean, Y. X axis? Like, Y.
Yeah, the day. Okay. All right. Let me explain this. All right. Good example. We've got our variable is number of days someone drinks out of the week. Okay, it's a numeric variable. It can take on the values 0, 1, 2, 3, 4, 5, 6, or 7. What do you think the most common value is going to be?
2.
1.
3.
Probably 0. Okay.
It depends if you're in college.
Depends on what.
Yeah, it depends on the population. All right. Okay. But probably 0. All right. If we just said, picked a random person off the street and said, how many days did you drink this past week? Probably 0 will be the most common. Maybe 1. Okay. All right. But you'll probably see more 0, 1, 2, and it's possibly bimodal. There could be a large peak at 7 days a week also, so 7 times 10. It could be. I'm not entirely sure. This is a good question. Okay, but I would say it would probably look something like this. Okay. With, not too many people drinking 3 or 4 times as there are people drinking 7 times a week as there are. Yes.
Often people travel in a year.
Yeah, that would be right skewed. Okay, weight, human weight, right skewed, okay? Average weight of a person is around 160 pounds, that's men and women combined, okay?
That'd be right skewed?
Right skewed, yeah. Is it possible for someone, okay, so if we say 160 is the weight that goes kind of in this middle, do we have people that weigh 500 pounds?
Yeah.
Yes, okay, not very many, but yes, all right? 500 pounds is how much above 160? It's like 340 pounds above 160, okay? Is it possible for someone to weigh 340 pounds less than 160? No, okay? You would have nobody that low.
That's the reason why it's right.
So it's right skewed, okay? Because it's impossible to be that far below as it is to be that far below. All right, probably spending too much time on this topic. But symmetric, left skew, right skew. My clock died here. All right, uniform. Looks like this. Meaning that all values are equally likely. Okay. Again, this is a numeric distribution. So this is saying all values that are possible are equally likely. So an example of that could be something like, what is the last digit of your phone number? Okay, that could be 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. And each number I would say is equally likely. Alright, so far in describing our distribution of data, we've talked about the center, we've talked about the shape. Okay, the last thing we want to talk about is the spread. So spread is an idea of how similar are the values we see, or are they very different from one another? Okay. So are the values we see similar to one another? Or are they very different? So in the military, they have the honor guard. Are you guys familiar? The honor guard, or it's or at ceremonies. So at military funerals or guarding the tomb of the unknown soldier, they have military personnel that wear very clean uniforms. They have a certain look, okay? You have to be within a certain weight range, a certain height, and these people are kind of the public representatives of the military. Do you guys know what I'm talking about?
No. Yeah.
Yes? No? All right. Well, anyway, in order to serve in the honor guard, you have to be within a certain weight range. You cannot be too heavy, you cannot be too thin, you cannot be too tall, you cannot be too short. Okay? And so there are very tight restrictions. On the other hand, to just join the military in general, you have to pass a physical exam and be able to perform certain physical traits, but as physical tests. But as long as you can do those things, your height and your weight don't matter as much unless it's extremely unusual. Okay, so as long as you're able to pass the test, your height and weight don't matter as much. Okay, so if we were to look at the height of people in the military versus people in this honor guard, okay, so let's look at height of people in the military versus height of people in honor guard. What would our distribution look like? I would say, as for height of people in the military, my horizontal axis would be different heights. The vertical axis would be frequency or how common. I would say it would look something like this. Being people of average height, being the most common. Some people are taller than that, some people are shorter than that, but most people are close to average height. As for the honor guard, our distribution would probably look something like this. Okay, I think they try to choose people who are slightly above average in height, but not too tall, and you aren't allowed if you're too short either. This would be, this is regular military. Do these two pictures make sense, or are these confusing?
The second one, I'm just wondering, like, so because there's a differentiation within heights, that's why there's still some who are shorter than others, that's why it's.
Yeah, so
it's not
if you
uniform.
go to the honor guard and you ask, if you line all of these soldiers up, they're not all going to be the same height. Some people will be taller and some people will be shorter, but you won't find anybody shorter than 5'9" or something, because that's the rule. And you won't find anyone taller than 6'4" or whatever, because that's the rule.
So it wouldn't be because
Uniform, I actually don't know exactly what it would be, all right? I doubt it would be uniform. It might not have this symmetric shape either, okay? But the illustration here is that which group has a larger spread in height? The regular military, okay? Here we are likely to see a wide variety of heights, whereas in the honor guard, the difference in heights, you won't have as much, okay? So we have more spread here. And less spread over there.
That's why I'm sorry.
Yeah.
The honor guard is a more narrow peak.
Yes, so less spread would be more
Because
narrow.
that indicates the narrow spread.
That's correct. Okay. So we have concept of spread, meaning we have the values are different from one another, or they're very similar to one another. And that would be the concept of spread. All right, so let's just test your understanding. All right, so describe the shape. Okay, so one thing is it's bimodal. And what else can we describe about the shape? It will be right skewed. Yes.
How is it right to you? Is it symmetric?
It is not symmetric because there's no spot where I feel like I could put a mirror and it looks like the same length and size.
Oh, so basically if, oh, okay.
Okay, and so, you know, again, where would the balancing point be? Where would I want this thing to be balanced? Probably somewhere around here. And this right skew indicates that I've kind of got this pointy tail over here on the right side, meaning I can have values that are much higher than the balancing point, okay, that are this far from the balancing point. But if I try to go that far below the balancing point, I don't have anyone this far below. Okay? Is that okay? Alright. And if you're trying to remember which side is right skew or left skew, just imagine if you were to cut this out and skewer meat, okay? Stab some meat. Which side would you use to do the stabbing? The skewer. Here you would use the right side. Okay? That'll help you remember, alright? As dumb as that is. Okay.
So I'm sorry, with that, it would be more spread then?
Yeah, I don't have anything to compare against for a large spread or less spread, so.
So you would have to compare something when you're working on the.
Yeah, so the spread is more of, next week we will learn concepts like the range and the standard deviation, which are ways to measure spread. Okay. But those measures, in of themselves, are not very useful until we have other numbers to compare them against. Okay. So if I say some man took a test and he scored 33, is that meaningful? No, you have no idea if 33 is good, if 33 is bad. Okay? If I told you 90% of test takers score between 20 and 30, and I told you this guy has a score of 33, you'd say, wow, that's a great score. Okay? So again, a lot of these things are only meaningful when we have a context in which to understand them. Okay? But, so when you do your homework tonight, all right, or this week, before next week, okay, make sure you do your reading and do the prompts. Wait, don't get up yet, okay? Let me just give you a few tips regarding your homework, okay? Don't do all the reading at once and then try to do all the problems. Actually, what I would recommend is read through a few problems and check, see if you can answer those problems on your own, just checking the notes that you've taken in class. All right, if you're unable to, turn back in the book, read the relevant section to answer the questions, okay? And then answer and try to answer your problems that way. Do statistics a few times this week. Don't wait till next Tuesday and try to do all of your homework in the morning. Sure, you might be able to get away with it. And actually, if you don't even do the homework, I won't even know. If you lie on a piece of paper and say you did the homework, I will believe you, okay? But the benefit is best when you do, a few problems on, I would say 3 or 4 times this week, okay? And review your answers. I try to explain.
It's the same sheet every time, right?
Yeah, it's the same sheet. You're just going to update it and say, this date and this homework assignment. Okay. Any questions before we say goodnight? No? All right. Have a good night. See you next week.